450 degrees below zero, a vacuum so profoundly sterile that a single stray atom of hydrogen might drift for thousands of years before grazing another physical particle. This is the baseline reality, resting just beyond the outer magnetic boundary of our solar system. Out here, the intense, roaring nuclear furnace of our sun is reduced to a pale, fading pinpoint, entirely stripped of its warmth and offering nothing but a cold, indifferent glare against the black. There is no friction to slow you down. There is no atmospheric sound. There is only a crushing, silent expanse that stretches outward in all directions, forming an architecture of nothingness so immense that the human mind simply shuts down when forced to confront its true physical dimensions. We are strictly biological creatures, engineered by millions of years of evolution to navigate a highly localized, fiercely terrestrial environment. Our neurological hardware was forged on the plains and in the forests of a small rocky planet. We are optimized to calculate the distance to a rushing river, the parabolic trajectory of a thrown spear, or the sudden sprint of a predator across the grass. We understand miles. We can comprehend the distance between coastlines or continents. Our brains are remarkably efficient at processing these earthly metrics, grounding them in physical exhaustion and time. But when we point our observational instruments outward and begin to measure the spaces between the stars, our cognitive machinery fundamentally breaks. The numbers become so impossibly large that they cease to hold any physical meaning. They become abstract data flashing on a screen, entirely stripped of the visceral weight they carry in physical space. We effortlessly compress the cosmos into a manageable mental model, imagining solar systems as neat little diagrams and galaxies as glowing frisbees, because the alternative, actually feeling the weight and the isolation of that empty space, is psychologically unsustainable. We look up at a crowded ceiling of stars and see a dense community of light. We do not see the horrific, unbridgeable oceans of darkness that separate every single one of those pinpoints. Consider the absolute speed limit of the physical universe. Light racing through the vacuum at 186,000 miles every single second. On Earth, this speed is virtually instantaneous. It is the click of a switch, a flash crossing the globe in a fraction of a heartbeat, creating the illusion of immediate connection. But out in the deep dark, that exact same velocity is exposed as agonizingly, almost pathetically slow. A photon born in the crushing core of our own sun must fight its way to the surface, a brutal, chaotic journey that can take 100,000 years, only to launch into the void and take 8 long minutes just to touch the surface of your skin. If you were to watch that same photon travel to our closest stellar neighbor, Proxima Centauri, you would sit in absolute darkness for over 4 years. And that is merely crossing the street in our immediate cosmic neighborhood. As we pull back further, the scale begins to fracture our intuition completely. The Milky Way galaxy is a sprawling, rotating disk of gas, dust, and hundreds of billions of burning stars. To traverse it from one edge to the other, traveling at that absolute maximum, unbreakable speed of light, requires 100,000 years. If early human ancestors had somehow launched a probe at the speed of light, when the very first anatomically modern humans were walking out of the Great Rift Valley, that probe would only now be reaching the opposite edge of our own galaxy. We look at deep field images of galaxies and see them as dense, glowing structures packed tightly together like sand on a luminous beach. But this is an optical illusion, a trick of the light collapsing three-dimensional depth onto a two-dimensional lens. If our sun were scaled down to the size of a standard white blood cell, the nearest star would still be miles away, and the space between them would be a freezing, irradiated wasteland devoid of any structure, purpose, or shelter. And yet, the space within a galaxy is positively crowded compared to the abyss that lies beyond its gravitational grip. Once you slip past the outer halo of the Milky Way, you enter the intergalactic medium. Here the concept of distance takes on a hostility that defies reason. The nearest major galaxy to our own is Andromeda. Through a telescope, it appears as a beautiful, ghostly smudge of ancient light. In physical reality, it is sitting 2.5 million light-years away. The light hitting our observatory lenses tonight began its journey before the genus Homo even existed on this planet. It crossed a void so incomprehensibly massive that entire species evolved, thrived, and went extinct in the time it took a single beam of light to bridge the gap. But these measurements, as staggering and alien as they are, represent a static universe. They are fixed points on a map that assume the ground beneath our feet is stable. The true existential horror of cosmic distances lies in the mechanics of the space itself. The void is not a passive, empty stage where matter simply rests in the dark. The space between the galaxies is a physical entity, and it is stretching. The fabric of reality is being pulled apart by an invisible engine, a dark energy that relentlessly drives everything away from everything else. The further away a galaxy is, the more space there is to expand between us, and the faster it recedes into the black. We are trapped in a local pocket of gravity, watching the rest of the universe sprint away from us at speeds that break our biological understanding of physics. There are vast regions of the cosmos already moving away from us faster than light can ever hope to travel, meaning their light has already been stretched into oblivion. They have crossed a horizon of no return, wiped from our sky forever, leaving us standing in the center of a slowly growing, inescapable quarantine. This quarantine is not a temporary condition. It is a fundamental law of our expanding universe. As we attempt to look deeper into the architecture of space, we find that our everyday intuition, the mental framework that tells us distance, is something we can conquer given enough time and velocity. Is not just inadequate, it is completely wrong. To understand why our common sense fails so spectacularly, we must look at how the concept of cosmic distance was dragged from the realm of philosophical speculation into the cold light of empirical science. For centuries, astronomy was limited by what the human eye could see through simple glass lenses. The stars were thought to be fixed points on a distant sphere, all resting at roughly the same distance from Earth. Space was seen as a cozy, ordered room. The first crack in this comfortable worldview appeared in 1838, when the German astronomer Friedrich Bessel achieved what many thought was impossible. He measured the parallax of a star called 61 Cygni. Parallax is a simple geometric phenomenon that you can test by holding your thumb in front of your face, closing one eye, and then switching eyes. Your thumb appears to jump against the background. Bessel applied this exact principle on a cosmic scale. He used the entire diameter of the Earth's orbit around the Sun, a baseline of roughly 186 million miles, as his two vantage points, observing the star at 6-month intervals. The shift he observed was microscopic. It was equivalent to looking at a coin from a distance of several miles. When Bessel crunched the trigonometric data, the result shocked the scientific community. 61. Cygni was not just far away. It was roughly 11 light-years distant. This was the first time humanity had ever calculated a precise distance to a star, and the sheer emptiness it implied was deeply unsettling. It revealed that the stars were not close neighbors, but lonely beacons separated by gulfs of nothingness that defied human experience. Yet this was only the beginning of our eviction from the center of the cosmos. Less than a century later, a quiet astronomer named Edwin Hubble, working with the massive 100-inch Hooker telescope at Mount Wilson, shattered our understanding of distance forever. In the early 1920s, the scientific consensus was that the Milky Way was the entire universe. A collection of fuzzy spiral clouds in the sky, known as nebulae, were assumed to be small clouds of gas inside our own galaxy. Hubble focused his attention on one specific cloud, the Andromeda Nebula. He was searching for Cepheid variables, a unique class of pulsating stars whose intrinsic brightness is directly linked to the rate at which they blink. By measuring how fast a Cepheid pulses, astronomers can calculate exactly how bright it actually is. By comparing that true brightness to how dim it appears through the telescope, they can determine its precise distance, acting as a cosmic standard candle. In October of 1923, Hubble found a Cepheid variable in the outer arms of Andromeda. When he calculated the distance based on the star's pulse, the math yielded an impossible number. Andromeda was not inside the Milky Way. It was nearly 1 million light-years away at the time of his calculation, a distance so vast that it meant Andromeda was an entirely separate galaxy, an island universe of its own, floating in a vast ocean of empty space. With a single photograph, Hubble multiplied the size of the known universe by millions. The Milky Way was instantly demoted from the entirety of creation to a solitary speck in an uncharted desert. The data Hubble gathered next would uncover the mechanism that makes these distances truly horrifying. He noticed that the light coming from these distant galaxies was shifted toward the red end of the electromagnetic spectrum. In physics, this is known as the Doppler effect, the same principle that causes the siren of an ambulance to drop in pitch as it speeds away from you. The light waves from these galaxies were being stretched out, meaning they were moving away from us. More disturbingly, Hubble discovered a precise mathematical relationship. The farther away a galaxy was, the faster it was receding. This is not because the galaxies are flying through space like shrapnel from an explosion. It is because the space between the galaxies is actively expanding. Imagine a loaf of raisin bread baking in an oven. As the dough expands, the raisins move away from each other. If you are sitting on one specific raisin, you will see every other raisin moving away from you. The raisins that are furthest from you will appear to move the fastest, not because they are running, but because there is more dough expanding between you and them. In our universe, the dough is the fabric of space-time itself, and it is expanding at a rate defined by the Hubble constant. This means that distance is not a static measurement, it is a dynamic, accelerating barrier. The space between us and distant galaxies is growing every second, creating a cosmic horizon beyond which we can never look. Our biological intuition tells us that if we travel long enough, we can reach any point in space. But the mathematics of an expanding universe reveals a brutal physical truth. There are parts of the cosmos that are already moving away from us faster than light, and they are lost to us forever. We are isolated by the very nature of space itself, trapped on a tiny island of matter while the rest of creation rushes into an unreachable abyss. If you are compelled by these merciless truths of the cosmos, if you refuse to look away from the cold reality of our universe, then you belong here with us. This channel is a sanctuary for those who seek knowledge without comfort, who want to understand the true scale of the dark. Do not let your curiosity drift into the void. Subscribe now and join us as we continue to map the terrifying boundaries of the inescapable night. The expansion discovered by Hubble was merely the preface to a much more profound cosmic limitation. As our telescopes grew larger and our physics matured, we realized that the expansion of space is not a uniform, gentle swelling. It is governed by an invisible, repelling force that defies our most fundamental theories of gravity. We call it dark energy, a placeholder name for a profound ignorance that permeates modern astrophysics. When we calculate the total energy budget of the observable universe, we discover that everything we can see, touch, and measure, every planet, every star, every glowing nebula, and every black hole, accounts for a pathetic 5% of reality. The rest is hidden in the dark, with roughly 68% consisting of this mysterious dark energy that is actively driving the universe apart. The consequences of this metric are devastating for our future ability to observe the cosmos. Because the expansion is accelerating, the cosmic horizon is actively shrinking relative to our position. Galaxies that we can see tonight through our most powerful instruments are slowly but surely crossing an invisible threshold. Their recessional velocity, driven by the expansion of space, will eventually exceed the speed of light relative to Earth. When a galaxy crosses this line, the light it emits can no longer bridge the gap between us. The space expanding between us is simply growing faster than the photons can travel forward. The light waves will stretch out, their wavelengths becoming longer and redder, shifting from visible light to infrared, then to microwaves, and finally into radio waves of infinite length. The galaxy will fade from our view, freezing like an object falling into a black hole before vanishing into absolute, unrecoverable darkness. This means we are currently living in a privileged moment in cosmic history. We can still see the remnants of the early universe. We can still look out and map the sprawling cosmic web of galaxies. But this window is closing. Billions of years from now, any intelligent beings evolving on a planet orbiting a dying star will look up at a completely empty sky. The expansion of space will have pushed every other galaxy beyond their cosmic horizon. They will see no stars outside their own local cluster. They will have no way of knowing that other galaxies ever existed, no way to discover the Big Bang, and no way to deduce that the universe is expanding. They will be trapped in an absolute solitary confinement, convinced that their small cluster of stars is the entirety of existence, completely oblivious to the trillion-island universes that have drifted out of their reach. The distances we measure today are not just spaces. They are the walls of a slowly closing cage, sealing us inside a localized bubble of reality, while the rest of the universe fades into an eternal, uncommunicative silence. To understand the true architecture of this silence, we must look at the physical structures that make up our universe, structures so incomprehensibly massive that they reduce our entire galaxy to the significance of a single grain of sand at the bottom of a dark ocean. When we map the cosmos, we do not find an even, predictable distribution of matter. Gravity is a relentless sculptor. Over billions of years, it has pulled galaxies together into sprawling clusters, and pulled those clusters into titanic filaments of glowing gas and dark matter. This is the cosmic web, a nervous system of light stretching across the void, and it is here, in the mapping of this web, that the scale of the universe begins to actively defy the human mind. Consider our own local address in this vast network. The Milky Way is part of a local group of about 50 galaxies. This group is, in turn, merely a small appendage on the edge of the Virgo supercluster. But in 2014, a team of astronomers mapping the exact trajectories of thousands of galaxies realized that Virgo itself was just a single branch of a much larger, monstrous structure. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a cosmic watershed. Just as water on Earth flows down the slopes of a mountain to form rivers that eventually empty into the sea, galaxies in our region of the universe are caught in a massive gravitational current. We are flowing along invisible rivers of dark matter, pulled by the combined mass of 100,000 galaxies. Laniakea spans 500 million light-years. To put that into a physical perspective, if you could somehow fly a commercial jet airplane across Laniakea at its top cruising speed, the journey would take you roughly 500 quadrillion years, a time frame millions of times longer than the current age of the universe. And yet we are being dragged through this structure right now. Our sun, our planet, and everyone you have ever known are currently in freefall, plummeting through the Laniakea supercluster at a speed of over 1 million miles per hour, heading toward a mysterious region of dense mass known as the Great Attractor. We do not know exactly what sits at the center of the Great Attractor because it is entirely obscured by the dust and gas of our own Milky Way, a localized blind spot hiding a gravitational anomaly of terrifying proportions. We only know it is there because we can measure the mathematical pull it exerts on everything, for hundreds of millions of light-years around it. But the horror of the cosmic web is not just found in these massive concentrations of matter. The true existential dread of deep space is found in the spaces between the filaments, the voids. If the filaments of the cosmic web are the sprawling highways and glowing cities of the universe, the voids are the desolate, irradiated deserts that separate them, and none is more unsettling than the Bhuta's void. Discovered in 1981 by astronomer Robert Kirshner and his team, this anomaly was found not by looking at what was there, but by meticulously documenting what was missing. Kirshner was taking a redshift survey, a core sample of the universe. He was observing a specific patch of the sky in the constellation Bhutas, measuring the light from distant galaxies to determine exactly how far away they were. When he plotted the data on a three-dimensional map, he expected to see a relatively uniform scatter of galaxies, a typical cross-section of the cosmic web. Instead, he found a hole, a massive spherical region of absolute nothingness. The Bhuta's void is a sphere of emptiness, roughly 330 million light-years in diameter. It represents a volume of space so staggeringly vast that it accounts for nearly 0.25% of the entire observable universe. Based on the average distribution of matter in the cosmos, a space of this size should contain at least 10,000 large galaxies. To date, astronomers have found fewer than 60, scattered across the darkness like isolated rafts in the middle of a dead ocean. Try to visualize the sheer physical isolation of a galaxy trapped in the center of the Bhuta's void. If the Milky Way were placed in its dead center, the distances between us and the nearest neighboring galaxy would be so immense that early astronomers would never have known they existed. We would not have seen a single other galaxy through our telescopes until the 1960s, when our instruments finally became powerful enough to pierce that level of deep, uninterrupted blackness. For the entirety of human history, we would have believed that our galaxy was the only object in an infinite, pitch-black universe. The conditions inside this void are as close to a perfect vacuum as physical laws allow. Out here, the density of matter drops to less than 1 atom per cubic meter. It is a freezer of cosmic proportions, bathed only in the faint, stretched-out microwaves left over from the Big Bang. If you were floating in the center of the Bhuta's void, looking out, you would not see a sky filled with stars. You would see absolute crushing darkness. The human eye would be completely useless, receiving 0 photons of visible light from the distant walls of the void. You would be utterly alone, suspended in a silent, freezing sphere of nothingness that takes light itself 300 million years to cross. The sheer mechanics of measuring these structures require a leap in observational engineering that borders on the impossible. We cannot simply take a photograph of the entire cosmic web. We have to map it using the brightest, most violent objects in reality, quasars. A quasar is the active, feeding core of a distant galaxy. At the center sits a supermassive black hole, an object weighing billions of times more than our Sun. As this black hole consumes surrounding matter, the friction and gravitational compression heat the gas to millions of degrees, creating a localized vortex of energy that outshines the combined light of hundreds of billions of normal stars. Quasars are the lighthouses of the early universe. Because they are so intensely bright, we can see quasars that are billions of light years away. But astronomers do not just look at the quasar itself, they look at the journey of its light. As the light from a quasar travels toward Earth for 10 billion years, it must pass through the invisible gas clouds, the dark matter filaments, and the cold voids that lie between us. Every time that beam of light passes through a cloud of intergalactic hydrogen, the atoms in the gas absorb very specific wavelengths of light. When that mangled, ancient beam of light finally hits the mirror of a telescope on Earth, astronomers pass it through a spectrometer, breaking it down into a rainbow. Across this rainbow, they see dark, missing lines, like a barcode. This is called the Lyman alpha forest. Each dark line represents a specific cloud of gas that the light passed through on its 10 billion-year journey. By analyzing the exact position of these dark lines, we can calculate how much the space expanded since the light hit that specific cloud, giving us a precise distance. We use a single beam of light as a 10 billion light-year-long fiber optic cable reading the shadows of invisible gas to map a physical architecture we can never hope to touch. Through this painstaking, cold mathematical process, mapping the absorption lines of ancient light, we discovered a structure that should not exist. In 2013, astronomers mapped a concentration of quasars in a specific region of the sky and uncovered the Hercules Corona Borealis Great Wall. It is the largest known structure in the universe. It is a massive cluster of galaxies held together by dark matter, stretching across an expanse of space so large that it shatters our models of how the universe formed. The Hercules Corona Borealis Great Wall is 10 billion light-years across. This number is easy to say, but it is physically impossible for the human brain to process. Let us try to force it into a tangible perspective. The Earth is 4.5 billion years old. Our solar system formed out of a swirling disk of dust and gas. The oceans filled with water. Single-celled life emerged, evolved into complex animals, survived mass extinctions, and eventually produced a species that built cities, split the atom, and constructed telescopes capable of looking deep into the night. All of this, the entirety of Earth's history, took 4.5 billion years. If a beam of light, the absolute fastest phenomenon in the physical universe, started traveling across the Hercules Corona Borealis Great Wall at the exact moment the Earth first formed, it would still not be halfway across. It is a structure so vast that it occupies over 10% of the diameter of the entire observable universe. It is a wall of matter whose sheer existence presents a severe mathematical crisis for modern cosmology. Our standard model relies on the cosmological principle, the assumption that on a large enough scale, the universe is uniform and homogeneous. Matter should be distributed relatively evenly. There simply has not been enough time since the Big Bang for gravity to drag together a structure that takes 10 billion years for light to cross. The mechanism required to build a wall of galaxies this massive, in the time frame allowed by the age of the universe, requires a flaw in our understanding of gravity, a misunderstanding of dark matter, or a physical reality even more bizarre and hostile than we currently calculate. We are looking at a shadow cast across the cosmos, a physical object that dominates our sky, yet defies the very laws of physics we use to describe it. It sits out there in the dark, an unyielding monolith of mass and radiation, mocking our attempts to box the universe into neat, predictable equations. This unyielding monolith of mass out in the darkness forces us to confront a chilling realization about our pursuit of cosmic truth. When we find structures that shatter our models of how the universe formed, it implies something far more terrifying than a simple miscalculation. It implies that the very ruler we are using to measure reality is broken. As we push our observational instruments to the absolute physical limits of the universe, we do not just find more space. We find a barricade where our most trusted laws of physics begin to actively cannibalize one another. Welcome to the ultimate existential impasse of modern astrophysics. We call it the Hubble tension, and it is a mathematical crisis that is currently tearing the foundation of cosmology apart. To understand why this is so devastating, we must look at how we establish the speed at which the universe is expanding. We have two perfectly rigorous, scientifically flawless methods for measuring this expansion. The first method involves looking at the relatively nearby universe, measuring the distances to galaxies using what we call standard candles. These are very specific, incredibly violent cosmic events, primarily Type 1a supernovas. A Type 1a supernova is a cosmic time bomb. It occurs in a binary star system where a dead hyperdense core called a white dwarf is slowly cannibalizing its companion star, stripping away its outer layers of gas. The white dwarf gorges itself on this stolen material until it hits a precise, unbreakable mathematical threshold known as the Chandrasekhar limit. The second it reaches exactly 1.4 times the mass of our Sun, the core collapses, igniting a runaway carbon fusion reaction that detonates the entire star. Because this detonation always happens at the exact same mass, it always produces the exact same peak luminosity. By measuring how dim the explosion appears from Earth, we can calculate its exact distance with ruthless precision. When astronomers use these exploding stars to measure the expansion of space, the mathematics yield a specific rate. The universe is expanding, and it is doing so at a blistering pace. But there is a second way to measure the expansion, and this involves looking at the absolute edge of the observable universe. We look at the oldest light in existence, the fading afterglow of the Big Bang itself. This radiation is called the cosmic microwave background, a faint cold whisper of microwaves that permeates every single inch of empty space. By analyzing the microscopic temperature fluctuations in this ancient light, scientists can observe the exact density and geometry of the universe when it was a mere infant. From this data, they project forward, using our standard model of physics to predict exactly how fast the universe should be expanding today. Here is the crisis that is keeping cosmologists awake at night. The two numbers do not match. When we measure the expansion using the dying light of supernovas in the modern universe, we get a rapid, aggressive rate of expansion. But when we measure it using the ancient radiation of the Big Bang, the universe is predicted to be expanding at a significantly slower, entirely incompatible rate. This is not a rounding error. This is not a slight smudge on a telescope lens. The discrepancy is statistically massive. Both measurements have been refined to a razor-sharp degree of precision. Both are considered absolute gold standards of modern observational astronomy. Yet, they fundamentally contradict each other. It is as if you are trying to measure the length of a dark hallway. You measure it from one end using a laser, and you measure it from the other end using a tape measure. And you get two wildly different lengths, suggesting that the hallway itself is shifting its fundamental geometry depending on which direction you look. The Hubble tension reveals a terrifying blind spot in our comprehension of reality. It means there is an invisible, unknown mechanism operating in the void, a ghost in the cosmic machine that we cannot see, cannot measure, and do not understand. It implies that dark energy, the invisible force driving the galaxies apart, might not be a constant feature of empty space as Einstein believed. It might be evolving. It might be growing stronger, accelerating the tearing of space-time in ways our current models of physics literally cannot process. But the paradox of measuring the cosmos goes far deeper than a disagreement over the speed of expansion. If you attempt to look past this tension, if you try to peer deeper into the darkness to find the ultimate origin of these distances, you hit a physical, insurmountable wall. Our intuition dictates that with a powerful enough telescope, we should be able to look back infinitely through space. But distance is chronologically bound to time. Looking far away means looking back in time. And when you look back roughly 13.8 billion years, you hit the ultimate dead end, the surface of last scattering. This is the cosmic microwave background we just spoke of, but it is not just radiation. It is a physical barrier in time. It is the absolute edge of the observable universe. To understand why we cannot see past this wall, you have to understand the brutal physics of the early cosmos. 380,000 years after the Big Bang, the universe was not the freezing, empty void we see today. It was small, compressed, and unimaginably hot. It was a chaotic, boiling soup of subatomic particles. The temperature was so extreme that atomic nuclei could not hold onto their electrons. The universe was completely filled with a dense, violently glowing plasma. In this state, light could not travel. The moment a photon tried to move, it instantly smashed into a free-roaming electron, scattering its trajectory. The entire universe was an opaque, blinding wall of glowing fog. It was physically impossible for light to cross any distance whatsoever. It was only as the space expanded that the temperature began to drop. When the ambient temperature of the cosmos fell below 3,000 degrees Kelvin, the energy threshold crossed a critical barrier. The universe cooled just enough for protons to capture those free electrons, forging the very first atoms of neutral hydrogen. In an instant, the fog cleared. The electrons were locked away and the photons were finally free to fly blindly into the expanding void. That specific moment, that flash of atomic creation, is the absolute limit of our vision. When we point our most advanced radio telescopes into the deepest black of the night sky, we are picking up the vastly stretched out, freezing remnants of that very first light. We are looking directly at the glowing, cooling wall of the early universe. We physically cannot look any further because, before that precise moment, there was no light traveling through space. There was only an opaque prison of boiling matter. We are trapped in an observational sphere, surrounded on all sides by the blinding, unyielding fire of our own genesis, and yet the human mind refuses to stop. We demand to know what lies beyond the wall. We try to calculate the distances, the densities, and the mechanics of the universe before the light broke free, winding the clock backward to the very first fraction of a second of creation. This is where the universe stops merely confusing us and begins to actively dismantle the very concept of distance. As we compress all the matter and energy of the observable universe back down into an increasingly microscopic volume, the two foundational pillars of human physics are forced into a horrific collision. For a century, our understanding of reality has been divided into two entirely separate kingdoms. On the massive scale, the scale of stars, galaxies, and infinite distances, we use general relativity. Gravity warps the smooth fabric of space-time. The math is elegant, predictable, and continuous. On the microscopic scale, the realm of atoms, electrons, and quarks, we use quantum mechanics. Here, reality is jagged, chaotic, and governed by strict probabilities. Particles pop in and out of existence in a frenzied, unpredictable foam. In our everyday universe, these two kingdoms never interact. Gravity is too weak to matter on a microscopic scale, and quantum chaos is smoothed out on a cosmic scale. But when you rewind the universe back to the first trillionth of a second, you are forcing the entire mass of the cosmos into a space smaller than a single proton. You are forcing the infinite weight of general relativity into the jagged, chaotic realm of quantum mechanics. When astronomers attempt to merge these two theories mathematically, the equations literally break. The math begins producing infinities. The concept of space itself collapses under the crushing weight of the singularity. At this ultimate extreme, we encounter the absolute limit of physical reality, the Planck length. This is a measurement so small it borders on the absurd, 10 to the power of negative 35 meters. It is a distance a trillion times smaller than the diameter of a single hydrogen atom. The mathematics reveal a merciless truth. Below the Planck length, distance ceases to exist. It is not that things get smaller, it is that the physical concept of between loses all meaning. The smooth fabric of space-time that we rely on to separate galaxies shatters into a violently churning quantum foam. Up, down, near and far dissolve into a mathematically undefined static. We spend our lives anchored to the belief that distance is a fundamental property of the universe, that no matter how far away a star is, the space between us is a tangible, measurable reality. But the deepest, darkest equations of modern astrophysics tell a vastly different story. Space is not a solid foundation. It is a fragile, temporary illusion, born from a microscopic chaos we cannot comprehend, stretching outward into a freezing void we can never cross, and ultimately bounded by an expanding horizon that is actively erasing the rest of creation from our view. If space is a fragile illusion born from microscopic chaos, then time is the ultimate casualty of this architecture. We move through our daily lives anchored by the comforting assumption of a universal present. We assume that right now, at this exact second, events are unfolding simultaneously across the cosmos. We imagine a grand cosmic clock ticking uniformly for every star, every planet, and every observer. But the extreme distances of deep space do not merely stretch light, they actively murder the concept of now. Because the speed of light is finite, the universe does not share a synchronized present. When you look up at the night sky, you are not looking at the universe as it is. You are looking at a localized graveyard of delayed ghosts. Consider the Andromeda galaxy again, sitting 2.5 million light-years away. If an alien intelligence in Andromeda were to point a miraculously powerful telescope at Earth right now, they would not see you. They would not see modern civilization, the pyramids, or the first human ancestors. The light currently hitting their lenses left this planet 2.5 million years ago. They would look at Earth and see a primitive, icebound world where early hominids are just beginning to strike stones together to fashion the very first tools. But the horror of this chronological disconnect goes much deeper, cutting into the very fabric of Einstein's relativity. Imagine you are sitting in a chair, entirely motionless relative to the ground beneath you. Now imagine someone walking past you down the street. Because they are moving and you are not, the angle at which their personal timeline intersects with the rest of the universe is microscopically tilted. On Earth, at human speeds, this shift in time is so infinitesimally small that it goes completely unnoticed. But when you apply this slight tilt over a distance of 2.5 million light-years, the mathematics compound into a staggering distortion of reality. If that alien in Andromeda stands perfectly still, their definition of now aligns roughly with ours, separated only by the travel time of light. But if they begin walking away from Earth at a normal, casual pace, the tilt of their timeline swings wildly. Across that immense gulf of space, their now suddenly intersects with Earth's past. For them, at that exact moment, the 19th century is currently happening. If they turn around and walk toward Earth, their timeline tilts in the opposite direction. Their now suddenly snaps into our future. For the alien walking toward us, human beings who have not even been born yet are currently living out their lives. There is no universal present. Reality is fractured, segmented by distances so vast that the past, present, and future are entirely dependent on how fast you are moving and in what direction. We are isolated not just by miles of empty vacuum, but by unbridgeable walls of time, trapped in our own localized chronologies, while the rest of the universe plays out in a completely inaccessible timeline. Yet, despite this profound isolation, the local mechanics of gravity ensure that our immediate future is locked into a violent, unavoidable trajectory. While the vast majority of the universe is being driven away from us by the acceleration of dark energy, Andromeda is one of the few exceptions. It is massive enough and close enough that its gravitational pull is overpowering the expansion of space. It is currently falling toward us at a speed of roughly 250,000 miles per hour. In about 4 billion years, these two massive island universes will collide. You might instinctively picture this as a cataclysmic explosion of fire and shattered planets, a celestial apocalypse tearing the night sky to pieces. But the distances between stars are so ruthlessly vast that this collision will be an entirely silent, ghostly event. If you were to scale our sun down to the size of a ping-pong ball, the nearest star would be another ping-pong ball sitting over 700 miles away. When the Milky Way and Andromeda finally merge, their hundreds of billions of stars will simply pass through each other like two swarms of bees flying through opposite ends of an empty stadium. The mathematical probability of even a single star colliding with another during this event is practically zero. The gravity of the two galaxies will distort their shapes, throwing long tails of gas and orphan stars deep into the intergalactic void before eventually settling into a single, massive, elliptical galaxy. Astronomers have already named this future home Milkdromeda. This new sprawling metropolis of light will be our final fortress. By the time Milkdromeda is fully formed, the accelerating expansion of the universe will have reached a terrifying milestone. The dark energy pushing the cosmos apart will have stretched the space between us and every other galaxy cluster to a point where they recede faster than the speed of light. The cosmic horizon will close around us like a tightening noose. Any civilizations that manage to survive into that deep future will look out into the void and see nothing. The cosmic web will be gone. The distant quasars will be erased. The faint microwave glow of the Big Bang will have stretched into undetectable oblivion. Milkdromeda will sit alone in an infinite pitch-black ocean with absolutely zero physical or mathematical evidence that anything else ever existed. But even this localized fortress is temporary. The most chilling consequence of cosmic physics is not just isolation, it is the inevitable, slow degeneration of matter itself. The universe is a machine running on a finite tank of fuel, and the engine is slowly winding down. We are currently living in the stelliferous era, the brief, vibrant window of cosmic history where the universe is filled with burning stars. Inside the cores of these stars, hydrogen is crushed into helium, releasing the brilliant energy that lights up the sky. But hydrogen is a finite resource. In about 100 trillion years, the very last clouds of star-forming gas will be exhausted. The colossal, bright blue stars will have long since detonated in supernovas. The smaller yellow stars like our Sun will have swollen into red giants before sloughing off their outer layers, leaving behind dead glowing cores called white dwarfs. The only remaining lights in the universe will be red dwarfs, the smallest and coolest stars in existence. Because they burn their fuel at an agonizingly slow rate, they can survive for trillions of years. But eventually, even they will flicker and die out. When the last red dwarf extinguishes its fire, the universe will enter the degenerate era. The cosmos will be a lightless graveyard. Milkdromeda will be populated entirely by stellar corpses. There will be white dwarfs, slowly cooling embers of carbon and oxygen. There will be neutron stars, hyperdense spheres of crushed matter spinning silently in the dark. And there will be black holes, sweeping through the dead systems like silent predators. Without the radiation of active stars, the ambient temperature of the universe will plummet toward absolute zero. The planets that manage to survive the death of their host stars will freeze solid, drifting aimlessly through a lightless void. Occasionally, a dead star will drift too close to a black hole and be torn apart, creating a brief, violent flash of light, a microscopic spark in a dying room, before the darkness instantly swallows it again. Over unimaginable timescales, stretching into quadrillions of years, the slow, relentless mechanics of gravity will cause the orbits of these dead stars to decay. They will either be violently flung out of the galaxy into the expanding abyss, or they will spiral inward, swallowed one by the supermassive black hole at the center of Milkdromeda. Eventually, even the white dwarfs will freeze entirely, their core temperatures matching the background radiation of the void, They will crystallize into black dwarfs, silent, dead spheres of compressed diamond and carbon, emitting no light and no heat. They will be entirely invisible, phantom planets drifting through a perfectly cold vacuum. If our current models of particle physics are correct, matter itself has a shelf life. Protons, the very building blocks of atoms, are predicted to eventually decay. It will take a timescale so long that the number requires more than 30 zeros to write out, but it is an inescapable mathematical certainty. The solid structures of the universe, the dead planets, the frozen dust, the black dwarfs, will literally dissolve. Their physical bonds will break down, turning into a thin, harmless mist of fundamental particles that drift apart into the expanding dark. By the time this happens, the universe will have entered the black hole era. Everything we have ever known, every planet, every structure, and every atom of solid matter will be gone. The only objects left in the entire cosmos will be black holes, sitting in absolute silence, separated by distances so incomprehensibly massive that they will never interact. But even black holes are not immortal. The mathematics of quantum mechanics reveal a merciless truth at the edge of the event horizon. Empty space is not truly empty. It is a boiling surface where pairs of virtual particles constantly pop into existence before instantly annihilating one another. But when this happens precisely on the boundary of a black hole, the brutal gravity can pull one particle inside while the other escapes. The escaping particle steals a microscopic fraction of the black hole's mass. This is known as Hawking radiation. It is an agonizingly slow leak. For a supermassive black hole, it would take a 1 followed by 100 zeros of years to bleed out. But the physics dictate a cruel acceleration. The smaller the black hole becomes, the hotter it burns, accelerating its own evaporation into the void. At the very end of its life, it will vanish in a final, sudden flash of radiation, leaving absolutely nothing behind. When the last black hole evaporates, the universe will reach its ultimate state, the dark era. There will be no stars. There will be no planets. There will be no black holes. There will be a gas of solitary, wandering photons and subatomic particles, stretched so thin by the expansion of space that they will never cross paths again. A single particle might travel for trillions of years without ever touching another physical object. The temperature of the universe will rest exactly at absolute zero, because there will be no matter interacting, no heat transferring, and no structures changing. The very concept of time will cease to hold any physical meaning. Time requires events to unfold. It requires a before and an after. In a universe where nothing ever happens, where everything is perfectly cold and infinitely spread out, time itself simply stops. The universe will not end in fire or a grand collapse. It will just stretch into a perfect, quiet, motionless void. To stand under a clear night sky and truly comprehend these distances is to accept a profound and irreversible eviction from the center of reality. For thousands of years, human biology and primitive philosophy conspired to convince us that the universe was a stage constructed specifically for our benefit. We looked up and saw a canopy of lights designed to guide our ships, dictate our harvest seasons, and map our mythologies. We believed that the vastness of the dark was merely a backdrop, a quiet theater waiting for human consciousness to finally awaken and give it purpose. The cold, raw data of modern astrophysics utterly dismantles this arrogance. When you strip away the romanticism of exploration and the comforting illusions of science fiction, you are left with a physical architecture that is profoundly, terrifyingly indifferent to your existence. The universe was not scaled for biology. The distances we have measured, the millions of light years between galaxies, the hundreds of millions of light years across the frozen voids, the tens of billions of light years spanning the cosmic web, are not frontiers waiting to be conquered by human engineering. They are absolute physical quarantines. They are mathematical barriers forged by the blind, relentless mechanics of gravity and expansion, ensuring that the fragile chemistry of life remains isolated, localized, and ultimately contained. We are a hyperspecific, biological anomaly, engineered to survive within a microscopic atmospheric shell on a single silicate rock, orbiting an entirely unremarkable yellow dwarf star. We process time in the frantic rhythm of heartbeats and lifetimes, frantically attempting to map a cosmos that operates on the slow, unfeeling timescales of atomic decay and galactic collisions. The very neurological hardware we use to calculate these distances is fundamentally incompatible with the reality it is trying to measure. And yet, the true existential weight of astronomy does not come from the realization that the universe is hostile. A hostile entity implies a localized intent, a conscious effort to destroy or repel. The terrifying truth of deep space is its absolute, crushing apathy. The void does not care that you are here. The expansion of space-time is not actively trying to isolate us. It is simply tearing the fabric of reality apart, according to equations that have been running blindly since the first fraction of a second of the Big Bang. The black holes that will eventually swallow the dead remnants of our galaxy are not malevolent predators. They are merely points of infinite density executing the passive, flawless laws of general relativity. We find ourselves awake in a very specific, highly temporary sliver of cosmic history. We are currently living in the brief, vibrant transition period between the fiery chaos of the universe's birth and the infinite, freezing silence of its inevitable death. We are the microscopic byproduct of a universe that is slowly expending its finite thermal energy. Every thought you have ever had, every civilization we have ever built, and every monument we have ever carved into stone is nothing more than a momentary, fleeting thermodynamic fluctuation in a cosmos marching relentlessly toward absolute zero. The telescope, then, is not merely an instrument of discovery, it is a mirror of absolute perspective. When we point our most powerful lenses into the dark and pull the ancient light of dying quasars down into our spectrometers, we are not just measuring the redshift of intergalactic hydrogen. We are measuring the exact dimensions of our own insignificance. We are staring directly into an abyss that was infinitely vast before the Earth formed and will remain infinitely vast trillions of years after our sun has burned down to a frozen, invisible diamond. There is no grand cosmic memory. When the accelerating expansion of space finally pushes the last distant galaxy beyond our cosmic horizon, there will be no record that they ever shared this sky with us. When the last stars extinguish and the universe enters the long, lightless degenerate era, there will be no evidence that the stelliferous era, with all its warmth and light, ever existed. The universe will not remember the Milky Way. It will not remember the human race. It will not remember that for a brief, microscopic fraction of cosmic time, a species evolved on a tiny blue rock and looked up into the dark, desperately trying to understand the sheer scale of the architecture that was silently burying them. We are completely, entirely alone, suspended in a silent void that stretches out to a mathematically impossible horizon, actively accelerating away from us into a future of perfect, endless dark. You can measure the distances. You can map the empty voids. You can calculate the exact speed at which the light is fading. But the space itself will simply continue to expand, silent, cold, and entirely unbothered by the fact that you are here.